Thanks for coming. So this week we have Dr. Jungho Ahn from KIAS, and this will be his last seminar talk before his flight to UK.
Yes.
At the end of this month, and he will talk about this Erdős-Pósa for cycles. Please.
Thank you for the introduction, and thank you all for coming here. I didn't expect this much people, so I'm getting nervous, but I will try best. I'm Jungho Ahn from KIAS, and today I will present my recent progress on the Erdős-Pósa theorem. This is a joint work with Pascal Golin in Slovenia, Tony Hyun in Rome, and Jungho Ahn in Hanyang University in IBS. So let me first remind the Let me first remind the theorem of Erdős-Pósa. Erdős-Pósa in 1965 showed that for every positive integer k, every graph G has either k vertex-disjoint cycles or a set X of at most big of k to k vertices. When you delete this set from the graph G, there is no cycles. So this talk is about the generalization of this theorem, and I'm interested in the following question as follows. So what if we consider cycles which are not only vertex disjoint, but also have no edge between them, between any two distinct cycles in C? So one natural attempt to extend the Erdős-Pósa theorem might be as follows. For every positive integer k, does every graph G have either an induced packing of k cycles or a set X? Let's wait for him to fix the problem. To the rescue. Yeah. He massaged the wire. Yes.
Yeah, everyone can just look here, right?
It's not that cable, it's like a point. It's not that connection. HDMI 그런데 안 좋은데?
모르겠어요. 이게 그 커넥션이 계속 끊기네요.
아니, 여기 거의 컴퓨터에서 오는
도움이 됐어요.
아니면 그냥 다른 제 걸로 해볼까요? 컴퓨터 문제가?
지금 어디부터 가지러 가는 거예요?
아니 여기에서 저기가 안 보이는데 여기
여기는 보여요. Okay. Sorry for technical issue. Let's keep going. So with this definition of induced packing, we may guess the following generalization of Erdős-Pósa theorem. Namely, for every positive integer k, does every graph G has an induced packing of k cycles or a set X of big O k to k vertices such that G delete X has no cycles? Does anyone believe this theorem?
When you say
No. Why? He shake the head.
If it were an actual theorem, then I think you will not.
Okay. I got the point. But actually, this is false because of a very easy example. Yes, the clicks. Now it okay. You can see that clicks have no induced packing of 2 cycles. And if we want to delete all the cycles, we have to delete almost all vertices. So it has neither a large induced packing of cycles nor a small set which hits all the cycles. But in this example, you can see that if you take just one vertex and delete all its neighbors, then you can see that there is no cycle remaining, right? So with this phenomena, we can guess the following. Can we either find a large induced packing of cycles or dominate all the cycles by a small set? And our main result is that this is true. So here is our main result, and I will use the definition of for a graph G and an integer d at least 0 and a set x of vertices, the bore of radius d around x in G, which I will denote by bgx, d, is the set of vertices of G which are at distance at most d from x. So you can see that bg x, 0 is nothing but x, and bg x, 1 is exactly the closed neighborhood of x. Then here is our first main result. For every positive integer k, every graph G has either an induced packing of k cycles or a set x of at most big over k to k vertices, such that if we delete the bore of radius 1 around x, there is no cycle. So this is the right answer. And moreover, we can find the induced packing or the set in polynomial time. We can actually prove this theorem for long cycles. So the main result 2 is of a long cycle. So for an integer L, at least 3, an L cycle is a cycle of length at least L. And we can show that for all positive integers k and L, where L is at least 3, every graph G has an either an induced packing of k L cycles or 2 sets x1 and x2 whose size is big over Lk to k and big over k to k, such that after removing the bore of radius 1 around x1 or the bore of radius L around x2, the resulting graph has no L cycles. So you can see that if we put L as a 3, this theorem is exactly the same as before. Is there any question so far?
So sorry, why we distinguish these two sets?
Just because of the size. So this one, the size of x1 depends on L in the first case, but the radius is fixed by 1. But in the latter case, the size doesn't depend on L, but the radius depends on L.
Yes.
Yeah. No question? Okay. Oh, yeah.
Why do I have 2 sets there? Like, if neither nor has an L cycle, can I just choose them the same?
No, but because their sizes are different.
Ah.
Yeah.
What is XP time?
XP time, yeah. It's in polynomial time when L is a constant. Yes.
What is the exponent like?
It's like n to the L plus 2 or 3, so it's quite moderate. Yeah.
Sorry, could you show the first result? Come back to the
Uh,
first result. So the quantitative result k times log t is optimal. Or
Yeah, it's optimal. Because
so that means this is the directly strength of the original Erdős-Pósa.
where original Erdős-Pósa only deleted the vertex at x, but we delete the ball of the or the closed neighborhood of X.
Or maybe you can subdivide every edge.
Yeah,
and
yeah,
then
yeah.
You can reduce the.
Exactly. So we can show that our theorem implies the Erdős-Pósa theorem. Yeah. So the function k rho k is optimal.
So this algorithm you have, the exponent only depends on L, right? Not on K.
Now, yeah.
Yeah. Do you think this is W1 hard in this setting? Or?
Good question. I didn't think about that. Yeah. Maybe, but not sure. Yeah. Yes. So this is our second result, and actually we can do further. We can now consider S cycles, and the definition is as follows: for an integer L, L is 3, a graph G, and now we consider a set S over vertices. Then an LS cycle is an L cycle containing at least one vertex from S. So you can see that L cycle is nothing but LVG cycle. And recently we showed that for all positive integer k and L, every graph G and every set S, G has either an induced packing of k LS cycles or two sets like before, whose size is big over L times k cube and big over k cube, such that those two graphs have no LS cycle. Also, we can find them in polynomial time when L is a fixed constant.
Can I ask a second question?
Yeah.
So the second set, this x2,
Yeah.
the size does not at all depend on L, right?
Yeah.
But you still need the x peak time to find this x2 set?
Yeah.
Because you need to somehow check if there's a long hole?
Yeah. That's
This
right.
is the hard part?
Yeah. We have to check whether there is some passive length, blah blah, which
okay.
depends on L. So
Yeah.
we still need this time.
Running time doesn't depend on size of S.
Yeah. Because the size of S is at most n, so yeah.
Sir, can x1, x2 intersect S set X?
Yeah, of course. They can contain some vertex from S.
Also, I have a question for your second main result. You consider L cycle for induced packing, but is there already known result for L cycle for just packing?
Yeah. There is a result for L cycles for usual Erdős-Pósa theorem, and the function, the size of the set X is a KL plus K rho K. So we are very close to the optimal bound for the usual Erdős-Pósa, but there is still a gap, and that is one of the open problem in the last slide. Okay, if there is no further question, okay.
In this theorem, the bound is LKQ. It is quite far from the original S cycle theorem.
Yeah,
This
yeah.
okay. I would believe that this is tight bound or not.
No, we don't believe that this is type bound. Yeah, well, that's the other question in the last slide. Thank you for spoiling all the open questions. You can now exit. Yes.
I have a question that should be on the last slide. For the natural attempt, so what you did is just kind of make a ball around your set that you delete.
Yep.
What if I restrict the graph that I look at? The natural attempt still works if I look at bounded degree via your theorem. Is there something else I can do?
For bounded degree, we can just show that. For bounded degree, this set has a small size, right?
Yeah, exactly. I'm
Yeah.
saying bounded degree obviously works. Is there something more general that I can?
Planar graph.
Planar graph?
Yeah, for planar graph, you can show that there is a set X of size at most 5K, which work for this theorem.
Does this work for general H-free graphs?
I don't know. Yeah, I
Okay.
don't know. We can naturally extend the method to H-free graph because we use. Maybe we can because we use Euler formula. So maybe we can, but I'm not sure.
But you don't know. So There's some obvious counterexamples like KT, KTT, but like do you have more interesting counterexamples where this doesn't work?
No, I didn't think about it more. So you want to forbid them, and you want to see.
No, I just want to know if you know other interesting counterexamples just to see what should be excluded.
No. I don't have any more. Yeah. So in the remaining of this talk, I will briefly give you a proof idea for these three main measures. And let me first give you proof outline for the first main measure. The proof can be summarized by 3 steps. And the first step is to construct a specific subgraph H where every vertex has a degree between 2 and 4. And with this specific subgraph H, we're gonna find one of the following. So the first one is a small set of vertices in H which dominate all cycles in G. So the first item is exactly one of the outcomes we want. So in this case, we are happy. And in the second item, if we cannot find this one, we're going to find the large induced packing of cycles in H. This second item, we are not fully happy because we want to find the large induced packing in G, but here we only find the large induced packing in H. So in the next step, we show that the packing we found is actually an induced packing in G when the coarse of G is at least 5. So these are the steps for the first main measure. And let me give you more details in step 1. I will first illustrate how to construct this graph H by figures, and then I will give you the formal definition for this graph H. So let's start. So I will first find the shortest cycle. And then I will add the shortest ear. After I attach a ear, I took a ball of radius 2 in the current graph H around the branch vertices. So I highlight them by purple colors. And can you see this color? Okay,
Yes.
good. Okay. So I take those vertices, and then I take neighbors of them in G. So I circled them by a red circle. And the next step is attach a new shortest ear which avoids these red circles. And we keep this process again. So after attach a new ear, we take red circles, and then we keep at a new ear which avoids the red circles, and so on. Okay, is it good?
Mm-hmm.
Maybe we are stuck at some point. It means that maybe there is no further ears we can add. In that case, I will try to find the shortest cycle which intersects the current H only at one vertex, like this one.
But there's no guarantee that such a thing exists, right?
If it exists.
Uh-huh.
Yeah. So I will first search whether there is a such cycle, and if it exists, then I add a shortest one. And then I keep adding shortest ears as before. So I add a new ear, like that. Maybe we are stuck again. What it means? It means that there is no further ear I can add. Also, there is no cycles intersecting the current H only at one vertex. Only in this case, I will add a new cycle, which is a vertex-disjoint from the current H. And then I keep at the shortest ear as before. Maybe such ear can connect these two, but I don't care. Anyway, I add a shortest ear again, and so on. And I will call H to be the final graph. Is there any question about the construction?
So this new cycle you add, it can be adjacent to a lot of stuff in the previous computer.
Yeah, yeah,
right?
in theory, yeah, in theory.
Just avoiding these balls that you.
Yeah, yeah, yeah.
Yeah.
But at least we know that this cycle doesn't touch this one.
Yeah.
Yeah. Okay. So
H is the final graph, but not including the red balls, only including the ears, right?
yeah, 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 yeah. Only years. So we don't count these vertices as a part of H. Yeah.
But the red vertices you count?
No. I mean purple vertices?
Yeah.
Yeah, purple vertices
These
are
are
in
fine.
H.
Yeah.
So every vertex in H has a degree 2, 3, or 4. So we don't consider this extra vertices in vector circles. Okay. Is there any question? Now let's give you a formal definition of H. I will use the definition of the H path, which we already saw in the last lecture. For a graph G and it's a subgraph H, an H path is a path P of G minus EH between two vertices of H, where no internal vertex is contained in VH. Now here is a definition of the curly graph H, which we will call a coarse ER decomposition. For positive integers t, mu1 to mu t, a coarse ER decomposition in a graph G is a subgraph H, which is formed by taking a union of a Pij, where each Pij is either a cycle or path. And it satisfies some specific conditions A, B, and C, which we will shown in the next slide. And for each pair I, j, I will use these notations. So the first Hij is the union of Pi prime J prime, where I prime and J prime is lexicographically smaller or equal to I, j. And Yij is by taking a ball of radius 2 around the branch vertices, and Z is formed by Y by adding the neighbors outside H. So you don't have to remember these weird formulas because I will give you a figure. So this graph is H12 because I add the P11 first and P12. So this graph is H12. And these purple vertices form Y12, exactly. So you can now see that Y I name it by the alphabet Y because it looks like Y. So you can easily remember this one. And now you can guess the set Z. What is the set Z?
Red circles.
Exactly. The red circles form the set Z. So you don't have to remember the formulas for those weird notations. You can just keep this image in your head. Now let me give you the statement for the conditions. So the first one is as follows. For each I, when we are at I minus 1, mu I minus 1 step, there is no further H passes. And if there is no H passes, I will move on to the I, 1 step and try to add a cycle satisfying the following. First, if there is a cycle intersecting the current H at exactly one vertex, I will add it. If not, I will just add a shortest cycle outside it. Okay? And the third condition is that for each I and J, where J is at least 2, I will add the shortest Hij minus 1 path. So you can easily follow that this definition formalizing the algorithm I presented. And if we cannot add more Pij, then we say that H is maximum. Any question about the definition? No? Okay. So we just completed step 1. What is step 2? Find one of them. A small set dominating all cycles or large induced packing. The first item is very easy because of the following lemma, saying that when H is a maximal coarse Euler decomposition and X is the set obtained from Y by adding one arbitrary vertex from each component of H, which are cycles, then G minus BG x, 1 has no cycles. The idea is very simple. If G minus BG x, 1 has a cycle, then we can attach more here or add a cycle, which contradicts the maximality of H. Okay? So what it means? It means that the purple vertices plus some extra vertices actually dominate all the cycles in G. So if H has a few branch vertices, then we are done, because the set X is also small. So we may assume that H has many branch vertices. And this is the end of step 2-1. Is there any question? No? There must be a question. How many? And that's the next question. How many branch vertices we want? And it depends on the theorem of Simonovich. We're gonna use this theorem, which say that there is a function sk of order k rho k, such that for every positive integer k, if a cubic multigraph has at least sk vertices, then it has a k vertex-disjoint cycles. We're going to apply this theorem to the graph H. And to do this, we assume that H has at least sk plus 30 times k minus 1 branch vertices. Why we need this branch vertices? Because to find the large induced packing in H, we first remove at most 30 times k minus 1 branch vertices, and then we apply Simonovich's theorem. So I will explain more about this step.
Yeah, Jungho, but your graph is not cubic.
Exactly. So that's why I removed some. Yeah. And to do this, I need some Coarse condition, as I said before. And this Coarse condition can be guaranteed by this easy argument. If a graph G has a small cycle C of length at most 4, then we can just apply induction on G minus BG VC, 1. If this graph has k minus 1, has a induced packing of k minus 1 cycles, then we are done by adding this cycle C to the packing, right? If not, it has a small set dominating all cycles, so we can add this. We can just add 4 vertices to this set, so we are done, right?
Maybe 2 vertices.
Yeah, okay.
That's nice.
So constant number. Yeah.
No,
So-
why would it work with just 2 vertices? It means like you removed all of the neighborhoods of C, so it means mass C.
Right. So yeah.
Yeah.
Thank you for pitching. So we can guarantee that G has a Coarse at least 5. And if we have this condition, we can show this lemma. Let G be a graph of Coarse at least 5, and let H be a maximal coarse Euler decomposition in G. And let curly I be the set of pairs I, J, where J is at least 2, and the ends of Pij are adjacent in Hi, J minus 1. I just collect this some weird pairs. Then we can show that if either T or the size of I is at least 2k minus 1, then we can just find the induced packing in G. So this case, we are super happy. So we just assume that both T and I are almost 2 times k minus 1. Okay? Now I will choose branch vertices which I'm gonna remove. So first, from H, I remove all vertices V, which either has a degree 4 in H, like Sebastian pointed, or some one end of some pi, 2, whose length is at most 1, whose length is 1, or there is one end of pij, where ij is contained in the set I. So I first remove all those vertices, those branch vertices, and then recursively remove the degree 1 vertices to ensure that the resulting graph has a degree 2 or 3. Okay? So here is some quiz. How many vertices I removed? For the first item, I removed at most t, right? Remember that t is the number of steps I did. Okay? And the degree 4 vertex is only caused by attaching a cycle, right? So degree 4 vertices are at most t number. And the second item is also at most t. Because I add v for I, 2, and I is at most t. And the third one is at most this number. So the total number I removed is 6 times k minus 1. Because each of them is at most 2 times k minus 1. And you can see that if we remove the one branch vertex, say of degree 4, so suppose that we removed this vertex, and then suppose that we are recursively removing degree 1 vertex. Then how many branch vertices we lose? We lose this one, this one, this one, this one. So all those vertices become normal vertices. So it means that whenever we delete one branch vertex from here, we lose at most 5 branch vertices in total. So it means that we delete 30 times k minus 1 branch vertices in total. So the new graph H prime now has at least sk branch vertices, so we can apply Simonovich theorem. And let's see the packing obtained by the Simonovich theorem. Okay? Remember that this packing is just a packing of a vertex-disjoint cycles. So we don't have any guarantee that this is induced packing in H. But the reason why we removed those vertices is because of this lemma. We can show that after removing those vertices, every packing of H prime is actually an induced packing in H. So it means that those vertices we removed are the most problematic vertices. Okay? So C is an induced packing in H. And this is the end of step 2-2. Any questions so far?
In the part where you bounded lower bounded the girth by 5 and use the lemma, so you can just basically bound the girth by any constant?
Any constant, yes.
And can you also bound the girth by some small function of k? Then would the lemma be improved and also it wouldn't cost a lot?
What do you mean by the lemma is improved? I think this is good.
Good.
So
maybe some get better constants than 30. I don't know.
okay.
Like,
Well, actually, in our paper, this one is 18. So I don't know how much you want to decrease the constant. And actually, this constant doesn't matter to show the order of the function. So yeah, it's fine. But it's correct that we can make the girth condition higher, so that you can do some math on it.
but it doesn't really improve.
Yeah. So what's the next step? Next step is that, okay, the packing C we found is actually an induced packing in G when the girth of G is at least 5. And this is directly implied by the following proposition. If C is not an induced packing in G, then what it means? We already know that this is an induced packing in H. Then it means that EG minus EH contains some H connecting two cycles in the packing C. But we can show that this set is empty. In other words, if G has a graph at least 5, then the graph H is an induced subgraph of G. So it means that the packing C is also an induced packing in G. Okay? So this is the end of the proof for the first main feature. Is there any question?
Do you have some intuition why this is true?
Yeah. Maybe I mean there are many cases, so I can give you the full.
Because of the construction of H, you use shortest path, right?
Yeah.
Okay.
Let me give you some idea. So suppose that this is H, and suppose that we has a chord like this. Then we can take this one instead of this one, and this one is shorter than this one. Unless this one is length 1, but I don't care about this case. So the reason why shortest choice is important is because of this proposition. Okay. Now let's move on to the next main feature, which is about L cycle. And let me remind you the statement. We show that there is either an induced packing of k L cycles, or we can find the small sets whose force hit all L cycles. So to prove this one, what we need is the right definition for the curly graph H. So to newly define H, I'm gonna use this definition. And from now on, we fix on integer L, at least 3. And for the graph G and its subgraph H, an L extendable path of H is an H path P with ends A and B, such that the sum of the length of the P and the distance between A and B in H is at least L. Okay, so maybe P is short. Then it means that the distance between them, between the ends of the P is long. Or if P is long enough, then it is already L extendable path. Okay. Now we can easily modify the definition of coarse decomposition. Because it's a slight modification, I just highlight them by red colors. So L coarse decomposition is the union satisfying the conditions A, B, and C, where H is the same as before. And for Y, I take bottom radius L minus 1 instead of 2. And Z is the same as before. Then the condition is that now you can guess all the definition. The first one is G minus Z has no L extendable path. And the second one is that instead of adding a cycle, we add an L cycle, satisfying the same conditions. And the last one is that in each step, we add the shortest L extendable path. So this is the new definition for curly H in our problem setting. And we also say that H is maximal if there is no more Pij we can add. Any questions so far? Why we needed this definition? Why it is good? Because we can show that every cycle in H is L cycle. So we can just follow the proof outline before. Okay? So let me briefly do this. We can mimic the previous lemma, which is about step 2-1. So we can show that if LH is maximal at coarse decomposition, and X is blah blah, then G minus BGX comma 1 also has no L cycle. So we can still assume that there is many branch vertices. And let's move on to step 2, this 2. Now we need this condition instead of a Girth condition. We want to ensure that the graph G has no cycle of length between L and 2L. So because if there is such a cycle, we can apply induction on that on this graph. So let's assume that G has no such cycle. Then we can show the same lemma. Yeah, so I just change this cycle and course to L something. And now our collection I would be the set of pairs I, j, where the ends of pi, j are distance at most L minus 1 in the previous graph. Then if either t or the size of I is at least 2k minus 1, we can show that G has induced vacuum of k cycles. So small, and we can remove a few branch vertices to find the packing C obtained by Simonovitch theorem. Okay, everything is almost the same as before. We can also show that this packing is an induced packing in H. This is a very easy part. So the final step, step 3. Which proposition we use? We use this proposition. We show that if G has a girth at least something, then H is an induced subgraph of G. So what would be the next guess for the L cycles? Maybe we want to show this one. If G has no L cycle of length at most 2L, maybe H is an induced subgraph of G. Do you believe this? It's false, actually. Because L coarse ear decomposition only consider long cycles. But if there is a chord like this one, this edge cannot be captured by the L coarse ear decomposition. So there might, in theory, there might be many chords in our new calligraph H. But we can show that, yeah. But we can show that, okay, there might be a chord, but if there is such a problematic edge, the both ends of the edge must be close to some branch vertex. This is the most important part in this long cycle version, so let me repeat it. If EG minus EH has an HAB between two vertices of H, then there must be a branch vertex X which captures both ends of the chord. And actually this is enough to show that C is an induced packing in G, because we know that when a branch vertex is made, we all know that the shape of the borough radius L-1 in H. This is just nothing but a subdivision of K13. And how many cycles can intersect this subgraph? Only one. So no matter how there is a chord like this, we already know that only at most one vertex can go in and go out. This one. So those chords are allowed to show that C is an induced packing in G. Okay, is there any question? Well, actually, there is another case, degree 4 case, but those things we already removed, so you can just ignore. Okay, is there any?
Would such a chord not also give you some cycle of length less than 2L?
Sorry?
Wouldn't you get a cycle of length less than 2L
Mm-hmm.
somehow?
Not an L cycle.
But it's not. But we have this Girth assumption. Maybe it's too short. Yeah, okay.
Yeah, maybe it's too short. Yeah, because
too short.
Yeah. That's right. Okay. So this is the end of the proof for main literature 2. So in the remaining 10 minutes, I will briefly explain main literature 3, which I repeat here. So we can find either an induced packing of k LS cycles or some small set x1 and x2 where some balls around them hits all LS cycles. And we can also find them in XP time. Again, what we need is the right definition for curly graph H. So here we will use LS extendable path. So LS extendable path is an H path P with the same conditions before, and with another extra condition, which consider the set S. So LS extendable path is a L extendable path which either contains a vertex from S or connect two vertices which are in distinct component of H minus S. So with this definition, we just modify the coarse ear decomposition definition like this. And because of the definition of LS extendable path, you can now see that every cycle of H is an LS cycle. So we can follow the proof step. But things are not that easy for S cycles. So, I will not give you the proof for the third result, but I will highlight why it is hard. So the proposition we use for L cycle is as follows. And it tells us that every chord of H is close to some branch vertex. If such kind of a phenomena happens, then we are happy. We can just mimic the profile outline. But this doesn't happen in our LS coarse ear decomposition setting. Here is a very silly question, which is H12. And there is some LS cycle, and I add a new ear. But now you can see that there might be a bunch of chords, and we cannot use them to extend this graph H. And those chords are very far away to each other. I mean, the ends of the chord is far away to each other. So anyway, we have to control these chords. So that's the first reason why this problem is hard compared to the previous ones. So for this, I will use, I need the definition of a fragile Pij. And I say that Pij is fragile if it satisfies the following. If J is 1, then Pi1 intersects the previous H, which is unique. And the unique intersecting vertex is not in S. So that's the first case, which looks like, and this is not in S. And the second one is that if J is at least 2, that is, if Pij is a path, then the end of the Pij is connected in H minus S. So they are in the same component. So for those Pij, I will call them fragile Pij. And the right proposition we will need in S cycle setting is the following. Let G and S be as before, and H be a maximal LS coarse ear decomposition. And suppose that G has no short LS cycles. And suppose that EG minus EH has some chord AB between two vertices. Then there is a pair I, J's satisfying one of the following. The first item is that the first item is similar to the previous one. There is some branch vertex X in Pij such that, this is 4. Yeah. Such that the bore of radius L minus 1 found X captured the both ends of the chord. So this is good. But in the second, A and B might be in PI1, which is disjoint from the previous H. And the third one is now very weird, is that Pij is fragile, and A and B are in distinct component of Pij minus S. And the fourth one is similar to this one, saying that Pij is fragile, and for some branch vertex X in here, A and X are in distinct component of Pij minus S, and the vertex B is adjacent to X in H. So let me draw some figure for the last item. The last item say that there is a Pij, and there is some vertex in S. And here is a branch vertex X. Here is our vertex A, and the chord looks like this one. And the third item is nothing but A and B, like this. So we can classify all the chords in one of them. And using this proposition, we can derive the third main result, but I will not give you the proof because I don't want to torture you guys. So here are the conjectures, which already spoiled by two guys. So both are about the optimality of the function. It is already known that there is a KL plus K rho K optimal bound for the usual Erdős-Pósa theorem. So I wonder whether there also is KL plus K rho K vertex set whose bore hit all cycles, all long cycles. And the second one is about LS cycle with the same bound. Okay, this is the end of my talk. Thank you.
Thank you. Any questions?
Okay. So you essentially say you can either find many disjoint cycles that are pairwise at distance at least 2, or delete few balls of radius 1.
Yeah.
What happens if I crank up the distance?
There is a very nice widget, very recent widget about 4 guys, and they show that such a distance D variant holds for function k to 18 times polylog k.
Ah,
yeah.
So it can be extended to arbitrary.
Yeah.
So, sorry, I'm still trying to build some intuition on these ear decompositions. So, okay, let's say I'm not trying to be optimal. So, let's say the graph has girth 100 maybe. And I change a bit your construction. So now the red circle, let's say I will take it of radius 10, so that I have some margin. Is it true that the only way you can have 2 branching vertices which are close together, so let's say 2 branching vertices in H which are, I don't know, at distance 10, is it true that the only way to have this is that the path between them actually disconnects the thing?
That's true. Yeah, when we have a logical condition, we can show that there is a unique shortest path of some length, because otherwise we can find the cycle of length twice the distance, right? So and this is one of the crucial observations we use in the proof. And even more, we can say that if H has 2 vertices, 2 branch vertices A, B, whose length is at most L minus 1, we can show that this is the end of some Pij. And this is another crucial lemma we use.
Yes.
Yeah.
Maybe we think about the old cycle version or more general.
Okay, first, all the cycle doesn't hold.
I mean, some other variant, yeah.
And main result 4 would be even cycle.
Yeah.
Yeah. So it's a yeah.
Some kind of half.
half integral.
Yes, why not?
I mean, how we can define half integral induced packing? Yeah, that's another question. Yes, we should define the right definition for it. And yeah, we are thinking about the even cycles, but we don't have any result for cycles of length 0 modulo 3 or 0 modulo 5 or any other prime. We don't have any result about that. This is very hard.
You mentioned something about the algorithmic consequence. I was wondering whether it's known whether hardness for like deciding whether you have induced packing of size k is known or
about that.
like or
well,
two
actually-
induced cycles, for instance.
Two
Induced
in-
packing of size 2.
That is asked by Seymour.
Ah.
Yeah. So he asked whether there is a polynomial time algorithm to find the induced packing of 2 cycles.
That wasn't that answered?
Are you? Or
I'm not sure whether it is proved or not.
So let me try to. I'm sure that it works if you. I think it should be XP in the number of induced cycles you want.
Okay, we can discuss later.
In the number of in the cycle, then that is polynomial time, right?
Yes.
Yeah,
so
polynomials
polynomials
two-
you are
two
asking for
cycles.
only 2.
Okay.
Well, there should be no
Because
existing.
the proof is that if I remember correctly, if you don't have a lot of induced cycles, then the number of paths, the number of induced paths in your graph is polynomial.
So.
But so you can just enumerate them all and test exhaustively.
Okay.
It's-
I'm sure this is correct if you don't have KTT. I think it's also correct in general.
Okay. Thank you. Thank you.
It sounds like a very basic question, but as I understand, your proof is algorithmic, finding shortest test, shortest year, and the decomposition. Is it known that finding shortest cycle or finding shortest year and every operations that you did is polynomial time?
Every what?
Operations that finding shortest cycle, shortest year, shortest LPS?
Is what?
Is that all polynomial time? I mean,
When L is a constant, but we didn't try optimize the learning time. But yeah.
it is polynomial. So
Yeah.
Right, any other questions? If not, let's thank the speaker.